Welcome to the Deep Dive, a special edition of the Artificial Quant podcast series by the Python Quants.
Great to be here.
Today, we're really diving into quite a fascinating article. It's from the February 2024 Journal of Finance.
That's right. The Virtue of Complexity in Return Prediction by Kelly, Malamud, and Zhu.
Yeah, and our mission today is really to unpack their, well, pretty bold argument, isn't it? That maybe complexity using machine learning in finance is actually better than the simple models we've relied on for so long.
It really is a fundamental challenge. I mean, for decades, finance has championed parsimony, build models with fewer parameters. The assumption was always simpler is better, avoids overfitting.
We were all taught that, weren't we?
Yeah.
Keep it simple. Complexity equals problems.
Exactly.
But this paper flips that.
Yeah.
They talk about complex models where P, the number of parameters, is actually bigger than T, the number of observations.
Right, PT. That's usually where traditional stats gets nervous.
Ah.
But it's exactly the regime where machine learning, really excels. It lets you build these incredibly rich, high-dimensional approximations of what might be a very complex, nonlinear reality out there.
And the theoretical findings are, well, pretty stunning. They argue that the simple models we favored actually understate how predictable returns might be.
Yeah, they make the case that we might be throwing away valuable information by insisting on simplicity. It's quite a thought.
So if simplicity isn't the answer, what is? Their argument hinges on complexity plus something else, right?
Absolutely. They show theoretically that expected out-of-sample performance, like forecast accuracy and portfolio gains, actually increases with model complexity. But, and this is the critical part, only if you apply appropriate shrinkage.
Shrinkage, like ridge regression. Can you maybe unpack that a little?
Sure. Think of shrinkage, like ridge, as a way to sort of tame the complexity. It penalizes very large parameter values, stopping the model from fitting the noise in the training data too closely. It helps it generalize better to new data.
Okay, so it's complexity, but controlled complexity.
Precisely. When the real world is complex, which finance often is, a more complex model with this kind of regularization just captures more of the underlying reality. The benefits outweigh the costs of having many parameters.
Right, and this leads to that really counterintuitive point about R-squared.
Ah, yes. They show a market timing strategy can be profitable, economically valuable, even if the predictive R-squared is negative.
Negative R-squared. That usually means the model is worse than just predicting the average.
Traditionally, yes. But here, they argue the Sharpe ratio, measuring risk-adjusted return, is a much better metric for these complex models. R-squared just doesn't capture the economic value properly in this high-dimensional setting.
They call it benign overfit, is that right?
Yeah, benign overfit. It sounds like an oxymoron, but the idea is that even a model fitting the training data almost perfectly can generalize well out of sample because of the inherent regularization, like how ridgeless regression picks the solution with the smallest norm.
So it's not just theory. Do they test this?
Oh, extensively. They did a big empirical study predicting the aggregate U.S. equity market return. They used those standard 15 predictors from Goyle and Welch.
Okay, the usual suspects for market timing.
Exactly. And they used random Fourier features to build architectures, effectively like neural networks, smoothly going from simple to very complex models.
And the results? Did they match the theory?
Remarkably well. Over that long CRSP sample, 1926 to 2020, they found market timing Sharpe ratios improving by about 0.47 per year. That's substantial.
Wow. And this was despite often getting negative R-squared values out of sample.
That's the key finding. Negative R-squared, but significant positive Sharpe ratios with t-stats around 3. It really supports their theoretical argument.
And what does this mean practically? Did the models learn anything useful?
Well, interestingly, the complex ML strategies tended to learn long-only behavior, sort of like Camel and Thompson suggested, but without being explicitly forced to.
Okay, that's intuitive.
And even more striking, they found the models learned to divest to get out of the market just before NBER recessions. They successfully anticipated 14 out of 15 recessions in the test period, purely out of sample.
14 out of 15. That's impressive.
It really is. It adds a layer of real-world validation beyond just the snaps.
So this flies in the face of Goyle and Welch's earlier findings, right? They concluded market timing with these predictors didn't really work out of sample because of those negative R-squareds.
Exactly. This paper revisits that and shows that even Goyle and Welch's own linear kitchen sink model, if you apply proper shrinkage and look at the Sharpe ratio instead of R-squared, can achieve a Sharpe of 0.46.
So maybe we were just measuring success the wrong way.
That seems to be the argument, and makes you question that old adage, Occam's razor, the idea that the simplest explanation is best. George Box's famous quote about parsimony.
Right.
Well, the authors here suggest that when models are inevitably misspecified, which, let's face it, they always are in finance to some degree, complexity might actually be a virtue. They provocatively say Occam's razor might be Occam's blunder in this context.
Occam's blunder. I like that.
Managed complexity helps approximate the true, messy, nonlinear world better.
So wrapping this up, what's the key takeaway for you, our listeners, in quantitative finance?
I think the big message is don't automatically shy away from complexity.
Yeah, it seems like a higher dimensional approach, provided you use the right tools like regularization, might unlock predictive power we thought wasn't there.
And it forces a shift in focus. Maybe we obsess too much about traditional accuracy metrics like R-squared.
And need to look more at economic value, like the Sharpe ratio.
Exactly. Especially when dealing with these powerful machine learning models.
So perhaps the road to better predictions isn't always paved with simplicity. Maybe it's about embracing complexity, but doing it thoughtfully and rigorously.
It definitely gives us a lot to think about regarding how we build and evaluate models in finance. A real paradigm shift, potentially.
Definitely food for thought.
Thank
Thanks for
you.
joining us on this deep dive.